epsilon x will be equal to 1 minus mu squared. And right now I'm writing is an equivalent formulation, equivalent description to that one. Okay, so either one, sigma x minus mu 1 minus mu sigma 1. Okay, and compared to the plane stress, Hooke's law. That is epsilon x equal to so you can see there's a little bit different in the arrangement. So depends on your engineering justifications. If you pick the wrong simplifications mechanism, then basically that will you could overestimate or underestimate the problem, because you can see they have the same format, but the material constant is a little bit twisted into individual one, right? So basically, since that the formulation is available in anywhere, and falling into your engineering justification, you need to decide which model will be appropriate for your applications, and that's the key. And so that is the summaries, and this is the summaries of our isotropic materials, and we started from three-dimensional, and then we have two spatial applications, plane stress and plane strain. And the next one, I want to talk about the general and isotropic materials. And isotropic material, that means, what is the definition for isotropic material? Isotropic material, just like the material properties is so uniform, and if you stretch it in any directions, the response of the material to your stretch will be the same. On the other side, if you're going to stretch the composite material, and then depends on which direction you stretch, the material response will be different. So in this way, composite material is not isotropic material. So now we're going to talk about the more generic, and this is a little bit beyond our traditional thing. So in these sections, my goal is to just give you a little bit taste about what is the non-isotropic, or we call it anisotropic materials. And then we would have a little bit more detailed illustrations, but in terms of the calculation, I won't get you too involved. Okay. So hopefully. Hopefully, so that is my goal. And otherwise, if you'll be interested, you can welcome to my NE 631 that just happened 1 hour before our class. And there I'm going to torture them. Okay, so here is the feeling. So as a isotropic material, we pretty much come to get into our intuition. We understretch, and then this material will be deformed or in lateral direction. But for material that is not isotropic, once we stretch, we could also induce the shearing angle. And that is, right now you can see that a little bit weird. Usually in our traditional mechanical material, we know that the shearing must be induced by shearing force. But here you can see for general and isotropic material, we can only use the axial loading to induce shearing. And that is the nature of this kind of the generic, the more general material. Okay. So again, everything can be governed by Hooke's law, and assuming everything is in elastic deformation, no plastic. Okay, plastic deformation, that means it's a permanent deformation. We won't talk about that one. We will, and at the end of this lesson. So Hooke's law for an isotropic material, what is an isotropic material? That means elastic constant, Young's modulus, is a function dependent. If, say, I have those fibers embedded, if I place the fiber entirely in this direction, and I put into, say, raisins, okay, and I cure it. So that means once I cure this, basically it's form of fiber, the fiber like the composite. Under these situations, Young's modulus in this direction will be different from the Young's modulus in this direction.
So it's what dependent again?
Direction dependent. Again, the keyword, only one keyword is this. Anisotropic materials, elastic parameters are direction dependent. Elastic parameters, direction dependent. That's it. Then how many elastic parameters? Young's modulus, Poisson ratio, rigidity modulus, which means E, nu, and G. Those are direction dependent. And which directions? X, Y, Z, or any orientations. Okay, and then from there we could have further discussions. But that's pretty much here. Okay, so pick up the two keywords: elastic parameters and direction dependent, or not. If those elastic properties are not direction dependent, then that's isotropic. Is what we have done so far. So that is a basic concept. So people will ask you what you have learned in any 494 from Dr. Chen about anisotropics that I don't know. I feel ashamed for myself and not for you. Okay, because I didn't deliver the right concept to you at the right time. So now I want to give a little more taste about how Hooke's law looks like for an isotropic material. The contents from this point onward will be a little bit messy. And actually this is the starting point of we call the theory of elasticity. And that is the foundation of the ME 631 advanced material. But so here you can see my goal is not to get you too involved in terms of the symbols or calculation, but I want to give you the concept. Okay? And so the way is this. And usually we're starting from the formulation, or we're starting from the description of the stress element. Stress element, just like this, here we have 9 stress components, right? And this one representing is the element in the x direction. And sometimes we use 1, 1, 1, 2, 1, 3, which means the 1 direction, 2 direction, 3 direction. Or we can use x, y, z, depends on your preference. Okay, and we adopt this one. And this is, and in terms of the math expression, this is the 3x3 matrix. So basically, tau ij is the tau 3x3, and this is the good for our calculation later. But for the fundamental, for the beginners, and the people maybe get used to using x, y, z. So it depends on which symbols you like. Okay, and even sometimes people like to use the normal stress. This is a normal stress. Okay. So that is, people like to use sigma, and that is our symbols we use in our the ES631. So that is the symbol you pretty much you will get most familiar with that. But anyhow, and we know that for the stress, although we have 9 stress components, but you remember at the beginning I mentioned to you xy equal to tau y of x. This is. They are the 2 different quantities of the stress element, but in magnitude, they both must be the same in magnitude, because everything is under static equilibrium. So under the static equilibrium, out of the 9 components, they should be symmetric. So if this matrix is symmetric, so that means we only need 1, 2, 3, 4, 5, 6. So we only need either upper triangle element, or you can use the lower triangle element. We only need to use at most 6. We can uniquely represent the status of the stress. Okay, so right now I'm talking about is the expression of the elements. So